Good afternoon. My name is Gonzalo Garde and I'm a PhD student in Public University of Navarra, Spain. I'm a member of the Gaze Interaction for Everyone research group in the same university. In this presentation, I will talk about our paper, Synthetic Gaze Data Augmentation for Improved User Calibration. The objectives of the paper are two. One, to analyze the balance between generalization and personalization in deep learning-based gaze estimation solution. And two, to study the effect of pre-training the model over different domains before training our system for our final application. We want to study if it is important that both pre-training and target domain are similar. In gaze estimation, personalization is achieved through calibration. Calibration is the process from which a system is adjusted to an individual intrinsic aspects. This step is important as some characteristics of the visual system that are key to correctly estimate the gaze cannot be directly learned from an image, and so it's necessary to adapt the system to each user. One of the ways to calibrate a gaze estimator is to present the user a grid of points, as the ones that we have in the top right figure, and then ask the user to stare to the points in a specific order. In the simplified model of the eye figure that appears in the bottom right, we can find one characteristic that cannot be learned directly from an image. In this model, we distinguish two axes, the visual and the optical axis. The angular offset between both of them is called the kappa angle. This angle, which is specific to each individual, and even different for both eyes and y and x axes, is one of the characteristics that cannot be inferred from the image and need to be calibrated. We define high-resolution systems as those that rely upon heavily controlled environment conditions, such as illumination or range of freedom for the user movements, and use specialized hardware to take the image from the eye's area, so the region occupies most of the image. Low-resolution systems don't have such control over the environment conditions and tries to use a more modest hardware. In both types of systems, calibration has proved to improve the obtained accuracies. The solution based on deep learning to address gaze estimation problems suffers especially from one limitation. To train a system using this approach, there are necessary many images, and if we speak about supervised learning, they have to be correctly labeled. For gaze estimation, this is an important aspect, as building this kind of databases is especially costly. Traditionally, other computer vision projects have dealt with these problems by taking different approaches. We will highlight two of them: to build synthetic environments to extract the images from, or to pre-train a model to solve a problem from a different domain and then transfer part of the features learned by this model to the new domain. This process is known as transfer learning. The basis behind the transfer learning approach is that part of the more general features that the network has to learn to solve the first problem can be of use to solve the second one. The more similar the two domains, the more features the model can reuse. The main frameworks to develop deep learning solutions offer easy access to already pre-trained models over popular datasets. These networks can be an excellent starting point for the rest of the researchers to build their own solutions. To study the effect that the domain from which we pre-trained has in our final model, we had to choose three databases, two for training and one as a target. ImageNet was chosen as a general-purpose database for pre-training because of the availability of high-performance computer vision models over it. It is important to point that we did not train over ImageNet, but use a pre-trained model as part of our network. U2Eyes was the database chosen as a closer domain pre-training database. The reason behind using U2Eyes, which is a synthetic database, over other well-known and big real-eye tracking databases, is that, as it is synthetic, it benefits from two factors: availability of images and the precision of the labeling. In this paper, we will only use the gaze point, but as landmarks of the eyes, rotation, position of the head, and kappa angles are also labeled in the database, they could be considered in the future. And as a target database, the E2HEAD database was used because of its resemblance with the U2Ice database. Talking about the preprocess of the image from E2HEAD and U2Ice, this sequence is followed. Initially, the images are rotated to normalize the roll component. The rotation is done using the angle between the horizontal and the straight line defined by the two outer eye corners. The next step is to crop the images. The bounding box to crop the images is created using the distance between the two outer corner eyes, so we do not crop by mistake part of the eyes. Then, padding is added to the image. The padding is necessary to ensure that all images have the same size, and this will speed up the training process. Furthermore, the padding equalizes the size of the image and adds some information that the network can use to infer the depth, as the bigger the padding, the farther the person is from the camera. Our network's architecture consists of a ResNet 18 as backbone, followed by a global average pooling layer and 4 fully connected layers. The ResNet 18 was chosen as backbone because of the following reasons. It achieves good accuracy when trained over ImageNet, which means that can extract useful features. With our current hardware setup for training, it is a network that can be trained within a reasonable time frame. And also, its weights when trained over ImageNet are available in popular deep learning frameworks. So now let's talk about the training part of the experiment. The training phase could be split in two blocks. A block that we will refer as a starting point, and a block that is called 12 trainings. We differentiate between two starting points, depending on which pre-trained model was used. We could use the model pre-trained over U2Ice or the model whose ResNet 18 backbone has the weights of ImageNet. For the sake of reproducibility, we provide a GitHub link where the two pre-trained models can be obtained. The objective of training with two different starting points allows us to study the effect of transfer learning as point in the objectives of the paper. Independently of the starting point, the model is then trained over images from E2HEAD. We run 12 different training phases for each model, varying the number of images present in the training dataset. With this block, as we vary the size of the training database from only calibration to a combination of calibration and generalization, we can study the balance between generalization and personalization. As we have previously pointed, calibration, e.g. adding images of the target user to the training dataset, has proved to obtain the best results in other gaze estimation approaches. Because of that, the training dataset always contains 34 images of the target user. The size of the training dataset is varied by adding or removing other uses from the database. A summary of this training process can be seen in the next table. The K parameter varies from 0 to 11, where 0 indicates that none of the subjects of the E2HEAD dataset has been included, except for the user to be calibrated, and 11 indicates that all additional list subjects are present in the training phase. Each additional user adds 130 images to the training dataset. The network was trained for 240 epochs, using the Euclidean distance between the estimated lookup point and the real lookup point as the loss function. To optimize the network, we use the ATTAC optimizer and a learning rate schedule based on the cyclic learning rate schedule. However, It could possibly be replaced by any other schedule to prevent the network from getting stuck. The test results obtained for the network's training are shown in a box plot diagram in the figure. In an orange box plot, the results were obtained when the network was pre-trained over the U2ICE dataset, the closed domain. In blue, the results obtained when the ResNet-18 backbone makes use of the ImageNet weights. The x-axis in the graphics represents the number of users used in the training phase. It goes from 1 user, the 34 images of the test user for calibration, to 12 users, the calibration user plus the 11 additional users. The white axis represents the angular offset in degrees between the estimated gaze direction and the subject visual axis. This angular offset is computed by measuring the distance between the predicted point in the grid and the real one, and then using the known distance between the user and the grid to calculate the angle. A summary of the results is presented in the next table, with both the median and mean values. From the obtained results, we highlight two cases to study: correlation between the number of training images and the precision of the estimation, and comparison of the results obtained for each of the pre-training methods. If we observe the results obtained from the ImageNet table, we see that the regression results for any of the pre-training strategies tend to worsen as the number of training images decreases. This is the expected behavior, as reducing the number of images available while training makes it tough for the network to learn the optimum parameters to solve the problem. When the max number of images are used, the network achieves first-class performance when adapting the regressor for a specific user, yielding results close to the ones achieved in high resolution, 1.5 degrees. When comparing the performance of both pre-training strategies over the full training range, we distinguish two regions. A first region where the number of training users is less or equal to 2 plus the calibration user, and a second region where the number of training users goes from 3 plus 1 to 11 plus 1. We will start our analysis in the second region. In this situation, the models trained with any of the two pre-training strategies have a similar performance, but slightly better for the ImageNet method. From the numeric results in the table, we observe a difference up to 0.17 degrees in mean. In this term, the models follow the trend exposed in the previous point, improving the results as the number of images increases. However, in the first region, the difference in the results obtained from one strategy over the other is significant, with difference up to 10 degrees. Our hypothesis for this behavior is that when the size of the training dataset is large enough for the ImageNet model to adapt to the new problem, it benefits from the more variability presented in real images from its pre-training, rather than the more limited variability of the U2ICE images. However, the models pre-trained over U2ICE are more robust to the lack of training images than the ImageNet models, i.e., they were pre-trained in a similar domain. They are more capable of continuing learning than the ones trained in a more general domain. From the obtained results, we conclude that results close to high-resolution systems can be obtained by using calibration in low-resolution systems based on deep learning. The importance of providing domain images during the training process has been confirmed, and also the benefits of pre-training the network in a closer domain instead of in a more general dataset, to compensate the lack of useful case data images that characterize case estimation problems. Thank you for your time. Don't doubt to ask any question you have, and enjoy the rest of the workshop.